Alright, as per a request I got, here's example 7, page 92-3. Let's get it started from the beginning. So a spinner is designed so that the probability it lands on red is 0.3. Jane has 12 spins. Find the probability that Jane obtains no more than 2 reds, at least 5 reds. Now, because this is in a binomial distribution chapter, obviously we're going to use the binomial distribution. But in an actual exam, they will definitely ask a question like, either justify the use of the binomial distribution or which distribution fits this best. And essentially what we have to do is do our 4 checkpoints. Are there 2 possibilities? There are fixed probabilities. Is there a fixed number of trials? And are the trials independent? And this one fits all of them. Either it's red or it's not. Red is 0.3, therefore not red is 0.7. There are 12 trials, and as far as we know, because it is a fair spinner, the trials are independent. In this question, they don't actually ask you for that, but it's good to know how to find that. So first of all, no more than 2 reds. We have to be able to read that. So first of all, we want to just write down that the variable x can be modeled by the binomial distribution of 12 trials with probability 0.3 of success. This in itself is a mark in an exam question, just writing this. It's a method mark. It can be implied by correct working, but on the off chance your working is incorrect, you might not actually qualify for this. So please do write that down. So what we're actually doing under this probability distribution is we are calculating the probability of getting no more than 2 reds. So what that means is 0 reds, 1 reds, 2 reds. So what I'm looking at is less than or equal to 2. We can either use our tables or use the calculator. It is actually a little bit more precise to use the calculator. So I'm going to go to the binomial cumulative distribution, hit variable, write x equals 2, n equals 12, p equals 0.3, and we actually get more detail than what the tables say. This is 0.2528153. 479, blah blah blah. Obviously if you do the tables, I think it cuts it off here, but they're looking for, I think, at least 3 significant figures, maybe in these questions 4, so it doesn't really matter what you use, but it is always nicer to use the calculator, seeing as you can find more detail and then store your values to A or B or C and then reuse them for calculations if you need to. The tables will come in handy for part C though, so they're not entirely useless. And then part B here says at least 5 red. What that means is 5, 6, 7, 8, 9, 10, 11, 12, all of those possibilities. So I'm looking at probability of x is greater than or equal to 5. Now, because of my cumulative tables and the calculator, we have to somehow change this to the opposite sign. So this right here is equal to 1 minus probability of x strictly less than 5. So this is me taking away 4, 3, 2, 1, 0. But again, my probability tables are in terms of less than or equal to. So because these are whole numbers every time, strictly less than 5 means less than or equal to 4, because there's nothing between 4 and 5. And this number is something that I can actually either look up in the tables or actually use my calculator for. So what I would actually do, I mean, if you really want to show your working, which is always a good idea, you again could use the calculator or the tables and say now x is equal to 4. What you're looking at is 1 minus 0.7236554696, blah blah blah. Now what's useful about the calculator is I can actually store this value to a variable. So I would write, I mean, you can see this, I'm going to write store and then I'm going to hit A, and now that is stored to A. So I can actually go back to menu and go to the calculation section and write 1 minus A, and it will give me an exact thing here, 0.2763445,304. Again, you can use the tables, so therefore you can cut it off at 3,7 and then just write those numbers down in the calculator and do 1 minus those, or I mean, if you really want to, do it on paper. But this function is very useful because it's actually on the calculator, it's cross-platform. You can store something in the statistical distribution section and then change sections and reuse that value in the calculation section, and probably others as well. So these are parts A and B. But this is kind of the run-up to the part C, which is probably more interesting and a little bit more difficult, and actually foreshadows what we are going to be doing in the hypothesis testing section. So again, we're just going to wipe this clean. Here we have part C, where it says Jane decides to use this spinner for a class competition. She wants the probability of winning a prize to be less than 0.05. Each member of the class will have 12 spins and the number of reds will be recorded. Find how many reds are needed to win a prize. Now, first of all, we are still using exactly the same context. The outcome is still going to be modeled by the binomial distribution with trial number 12 and probability 0.3. This will still come in handy. But the different thing is here, essentially Jane is deciding on a new couple of rules, and she says that in order to win the game, you need to have over a certain number of red results. So for example, if she said that you needed to have at least 5. The numbers that would win would be 5 reds, 6 reds, 7 reds, 8 reds, 9 reds, 10 reds, 11 reds, 12 reds. Those would all be winning numbers. Now what she's doing, instead of setting a number of reds, is actually setting the probability. This is actually how a lot of casinos work, where they actually say they want it to be extremely unlikely to win. So Jane decides that she wants the probability of winning to be 5%, and then works backwards to figure out how many reds that corresponds to. So what we're actually looking for is the probability of getting a certain number of reds or higher. So we're going to set the number of reds. Let's say the winning number of reds is R. If I get R or more, so if that is 8, then it's going to be 8 or 9 or 10 or 11 or 12. I want to make sure that the probability of winning in general, so the probability of getting that number or more up until 12, needs to still be, all of those together need to still be under 5%. So what I'm actually calculating here is, what I want is the probability of X greater than or equal to this number of R. So that's the number of reds that allow me to win, and higher, because if I get more than R reds, then I'm still winning, because that's kind of the minimum. I want to make sure that that is less than 0.05. If I were using the calculator, I'd be using trial and error. I'd just be trying a bunch of stuff and figuring out where the border is. What we're actually going to use is the tables, because this actually allows us to see everything. In succession, we could use the list function on our calculators, which is exactly the same thing as the tables, although the tables are already printed out for you on the formula booklet and at the back of the book. But in order to use the tables, we need to reverse that sign again. So what I'm going to look for is P of X strictly less than R. And that, essentially, if I look for the kind of the border, let's pretend the border is there at 0.05, then this is going to be 1 minus 0.05, which is going to be 0.95. So what I'm actually going to do is I'm going to look up the tables with that probability on it, and I'm going to see where does the number go over 0.95, because that is the thing here. If this has to be strictly less than 0.05, what we're actually looking for is the value of R that takes me just past 0.95, because what I'm actually doing, if this is all my probability, I'm cutting it here, and I have my 5% and my 95%. These are all the probabilities of me not winning, and I just want to essentially cut it off there and make sure that I have the top percent, and this is where my R will allow me to do that. Now, it won't be exactly 5%, it never will be, but because it has to be strictly less than, we're essentially going to look for the first number that is less than 0.05. Therefore, if I'm going in the other direction, I'm looking for the first number that goes past 0.95 into the 5% territory. So we literally are just going to browse. If I look at the tables in either the formula sheet or on the book, we get this. And you might not be able to see very well on the screen, but you just get a list of probabilities. I look for 0.3, I look for n equals 12. And I've only written down 4 to 8 because that's where the interesting stuff happens. What I'm looking for is when does it go over 0.95, and that break happens here. Because probability, and again using the notation in the book of x less than or equal to, because that's how the probability tables work, 6 is equal to 0.9614. And that is the first value that actually goes over my 0.95. So this is the value I'm interested in. So what I need to do is I need to then translate this and flip the sign over again. So what this tells me is that 1 minus p of x less than or equal to 6 is going to be equal to 0.0386. Now if I had done this with this number here, I would have gotten 0.1178, which is still greater than my 5%. So this is really the first value that goes into the 5% range at the top. However, I then need to rephrase this again just to make sure that it fits this format here, the number of reds or above. What this is equivalent to is p of x strictly greater than 6, which tells me that if I get more, strictly more than 6, I win, which tells me that what I'm actually interested in is p of x, again, because they are whole numbers, this has to be greater than or equal to 7, is equal to 0.0386, which is the first value that is strictly less than 0.05. So which tells me that this is kind of the pivotal point. And we're actually going to use this logic to find critical values in critical regions when we're dealing with hypothesis testing, so this is important. But what this tells me is here, essentially, the odds of getting 7 or 8 or 9 or 10 or 11 or 12 all together are less than 5%. So the answer to this question is how many reds are needed to win a prize. To keep the probability less than 0.05, the answer is 7 reds. I hope that was helpful. Good luck.